V, like this?
No.
Sorry.
Sorry.
It's rho. I got you. E to the minus, go ahead.
0.01 T.
All right, so it's really T over 100. Go ahead.
At A rho.
Is that amps per meter squared?
Yes.
Go ahead.
It says find the charge density after 10 seconds if it has an initial value of 0.
All right, so he's saying that the rho V at times T equals 0 is equal to 0. Now, this is kind of a classic problem, but if you don't do them, a lot of people won't know what to do. Y'all with me? So I want to take you through it. There's two equations we talked about on Friday that are important. The first is divergence of D plus the rho V dt equals 0. And we also went ahead and said, well, actually, let me do it this way. Let me take you back one step. Let's set this right. I put down that curl of H is equal to J plus the partial of D with respect to T. Now, do you all remember that? Now, are you okay with that? This is standard. Now, after that, what I'm going to do on this equation, there's two things that typically happen. The first is take a divergence of both sides. Divergence of a curl is 0. So if you do that, take the divergence of curl of H. By definition, it is 0. That's equal to divergence of J plus d dt of divergence of D. Now, you can take the divergence operator inside the time domain, because this is assumed a linear system. In other words, the D field is not going to be a function of time in the sense of positionally a function of time. Y'all with me on this class? Now at this point, I'm going to tell you that there's two things you need to know. One is J is equal to sigma E, and the second is D is equal to epsilon E. Now, these are just equations. I call them coupling equations. You all with me, class? Everybody? Now, at this point, there's something that's important. You can see that J here can be rendered as sigma, and E can be D over epsilon. The only thing I'm doing is rearranging things to give you some insight. Y'all with me? Now, here we're given J. We're given this. Divergence, I'm going to put this down too. Divergence of D is what, class? Rho V, it's the volume charge density. That's really what we're after here, isn't it, class? How many understand that? That's what we're after. Now, just take a moment, think to yourself. We're after rho V. We have J given to us right here. It's given as this equation. It's in cylindrical coordinates. If we take a divergence of that, then we have that term, divergence of J. Everybody follow me on that? We can get this term, and I'll put this down. Div D is rho V. That's what we're after, right? So I can say that I'm just taking this equation, rearrange it. I can say D dt of, now I'm going to replace div D with rho V, is equal to, and this goes to the other side, minus divergence of J. Now, I hope you appreciate what I'm trying to do is let you see the steps that are logically you're going to take. We're after rho V of T, so if we can get the time derivative of it, we can integrate with respect to time and then solve for the actual value versus time. You all with me? Everybody? It should be logical. It should make sense. What's the divergence of D? Well, I mean J, pardon me. The divergence of J is what? Just take a look at that for a second. Look, what coordinate system, class? Say again? Just look at it. What coordinate system? What has rho in it? Cylindrical. Is it only a function of rho? Rho is only a function of rho, right? I mean J is only a function of rho. It's in the A rho direction. So if you look in the book, the divergence of this J, because the other two derivatives, Z, there's no DJEZ, right? No DJZ of DZ. There is no, what? There's no J as a function of phi either, correct class? So this becomes what? 1 over rho dd rho of what? Rho times that J, right? Which would be rho times the quantity rho e to the minus t over 100, right? And that would be the divergence of J. Would you do me a favor, if you have your books, just look at the back cover and look and see if you can spot divergence of J to make sure you see this and when I go. There are people that they will not understand even where this is coming from. And a lot of times, some of them are too shy to ask, but y'all follow. Do you have your books there or not? How many do? Look at the back cover. Look at cylindrical coordinates, divergence J. It'll say div J, I think, in there. Y'all see this, what I've done? How many do? 1, 2, do you see it there? Guys, or not? Look at the back cover. You see that? I mean, the very back cover. I mean, inside the back cover. Do you see it or not? Do you see it?
Yeah.
Okay, I'm just making sure everybody sees it. You don't have a book. I wish you'd bring your books. Anyway, what I'm trying to say is this is stated explicitly. So what is this going to be? Well, you all see the 1 over rho stays, right? Now I have e to the minus t over 100. That is not a function of the positional vector or position rho. You can take that out in front. All right. Now I have rho squared. Don't I, class, inside there? What's the derivative of rho squared with respect to rho? 2 rho. You can see the rho's cancel. Can everybody follow me on that? In the back, can you see it okay? And over here, you guys see it? All right. So now I come over here and I can say that this, the rho v dt, is equal to minus, and it's really e to the minus t over 100, right? We want rho v as a function of t. He gives us the value of rho v at t equals 0. Does he not, class? So what are we going to do to get rho v as a function of t? We're going to integrate. Do you agree? How many see this? If we have the time derivative, we want the actual value of rho v. Just integrate both sides. If we do that, what do you get? Rho v of t is what? It would be, what's the integral of that? 100, is it 100, right? 100 e to the minus t over 100. You all agree? But
you have an extra 2 from the rows cancel, but you got the extra constant 2 on the other.
Actually, you're right. I need a 2 right here. I'm sorry. So this would be 200. You're absolutely, who said that? You're right. Who said? You did? I don't know who said, but you're right. Thank you very much. From the very back, I'm glad you can read my writing. Y'all with me, class? Sorry about that. I don't mean to stop you. Okay? Now, if you have that, remember, you have to add something. I had a professor who used to always say, you have to add Charlie. You have to add a constant because we don't have definite limits on the integration. If we did, then we wouldn't. Y'all with me? Everybody? Now we have to evaluate that constant, don't we? How do we do that? Read the problem. What does it say? It's given. At t equals 0, what does it give you? Say again? Oh, 0. The charge density is 0. So what do we do? This is, and I better erase that computer there. This right here is true, but this is 2, right? Now we evaluate c at t equals 0. At t equals 0, it is 0. So we have 0 on this side equals 200 because e to the 0 is 1 plus c, or c itself is equal to minus 200. I want to make sure you see these steps. Is everybody with me on this? Trust me on this one. This kind of problem will cause people to go, I don't know what to do. I'm trying to help you now. If you haven't really done these, realize this. There's several different things I can do. I can give you charge density. I can give you J, I can give you D, I can give you E as a function of time, and initial values, and you'll need to get all the other quantities. Do you all follow me, class? So be aware of that. It's not just, I'll give you a problem identical to this. So when we get this, he finally asks for what? Rho v at what, class? T equal, say it.
10 seconds.
At 10 seconds? So what's this going to be? Well, it's simply this equation. We replace C with minus 200. Do y'all agree? So we simply say what? We're going to have, I guess I can take 200 out in front. And I have e to the minus, and this is going to be 10 over 100, right? And it's going to be that minus 200, right? So what's that going to be? Minus 1, pardon me. Factored out. I factored out the minus 200. Do y'all agree with this, class? I'm just rearranging things. Now what's this going to be? So, I don't know. What is that? That's 200, and it's going to be e to the minus 1/10 minus 1, so it's negative. Can you tell me what that is? Anyone? Anyone at all?
Negative 19.
Minus 19? Anybody confirm that? I don't know. I trust you, but I'm just making sure. Yeah. What is it? It's minus something.
Yeah, I got negative 19 as well.
Say again?
I got negative 19 as well.
Anybody else? I trust you. Okay, good. What's the answer? I don't know.
Negative 19.
Okay. But you follow me on this one. It's not that hard. It can be a little tricky if you're not paying attention. Are you with me, class? How many tried that one? Anybody? 1, 2.5?
I had trouble with it.
But you understand the process?
Now I do better now.
It's not hard, but you do have to do a temporal integration, and you have to take the divergence in cylindrical coordinates. Most of the time, it's just being attentive to get the right answer. You can see the method. It's not like you're lost and don't know where to begin if you do this. All right, that's that problem. Got a question for you, a little different question. Well, now the only way charge is going to be reduced, you see how the magnitude's going down versus time, is if there's a conductivity. Y'all with me, class? Now, he doesn't state explicitly what the conductivity is, but if you needed to get that, how would you get the conductivity? Well, I better not say too much. It gets a little tricky at this point. Anyway, there are several other things that we're going to talk about that relate to that type of problem. Now, getting back to boundary conditions, you asked, you mentioned boundary conditions. Which problem would you like to see? Anyway, how many tried boundary conditions? Good. I mean, really, it's in your best interest to do them. If you don't, you're really
Can
you're
I
hamstringing yourself.
4.52 if
Okay.
possible?
Let's take a quick look. Okay. So for 4.52, I did put the solutions up, right, for these? Y'all with me? Aren't the solutions for chapter 4 up?
Chapter 4, yes.
Right. So, if you take a look at this, chapter 5 is it? Would you send me an email? I'll put them up as soon as I'm done. I apologize. Usually if I give you problems in a chapter, I provide solutions. Now, the truth is this. The solutions are all over the internet. There's PDFs of the solutions manual everywhere. I can't tell you a place to get them because I got a copy. But I know that they're out there. My students will come to me sometimes and just have a solution manual ask me about it. So it is available, but I'll post it for you. So for 450 or 452, can you tell me the specifics?
Yeah, so it says the XZ plane separates magnetic material with mu R1 equals.
All right, we'll call this X, Z, and that Y, right?
Yeah.
Go ahead.
Separates magnetic material with mu R1 equals 2 for Y is less than 0 from
All right,
magnetic.
so down here on this side of this XZ plane, right here, we got mu relative equals 2. Go ahead.
And then mu R2 equals 4 for Y is greater than 0.
Mu R2, call it mu R1 equal 4. Go ahead.
Alright, in medium 1 there is a field H1 equals 2.
1, 2. All right, so here H1 is what?
2AX plus 4AY plus 6AZ amps per meter.
6 AZ.
Mhm.
Go ahead.
And it says find H2 assuming the boundary has a surface current K equals 2AX minus 2AZ.
Okay, so right here we have a surface current K equal what?
2AX minus 2AZ.
I'm assuming the units are amps per
You
meter.
wrote AX twice,
Huh?
I think. I think you wrote AX twice for K.
Sorry. It's 2AX minus 2AZ, right?
Yeah.
Everybody with me on that? Now, what are the boundary conditions? Go over them in your head. First, do the tangent. What is always the tangent going to be? H tan in region 1 is H tan in region 2. Does everybody follow me? Now, the tangent is what? They're the fields in the plane, or the projections of the H field in the plane separating the two regions.
Wait, isn't H10 1 equal to H10 2 only if K is, there's no surface current?
Always, right? If K, I'm sorry. Oh, let me do it this way. You're actually, you're right about that. I'll go to the normal first. And I want to tell you where these are in the book. We'll do B normal 1 is B normal 2, but I want to make sure I understand, or I say this correctly. I apologize for that. So I was going to do this without the currents first. Did he ask without the current first? Or
No, he
okay.
just asked.
The last problem we did, like you had no current, then current. Sorry. So for this one, it's 478 is the equation. I'm going to go first. And I just want to do this. I go for the ones I don't have to worry about surface current. So B normal in region 1 is B normal in region 2. I told you tangent is in the plane, right? What is normal?
Where the
It's perpendicular to the surface separating, right? If you look at this, can you all see that the normal to this plane would be simply AY? It would be that, so it's the Y component on either side of the B field. You all follow me, class? How many see that? All right, so what is B normal 1? The Y component right here is 4AY. Do you agree? Right? But that's what? That's H. For the normal component of the B field, we'd have to multiply that by mu0 times mu relative. Do you agree? So here, we would say, really 2 mu0 times 4. So that's mu times the B field in region 1 have to be the B field in region 2. Well, the B field in region 2 is going to be 4 mu naught. The only thing I'm showing you there is it's 4 and mu naught, mu is equal to mu relative mu naught, so it's 4 mu naught times the H field in region 2. And this would be H tan in region 2. It's got to be HY. So if you look at this, HY in region 2, there's going to be simply what? It's going to be 2 divided by 4, it's going to, or it's 2 divided by, or 2 times 4 divided by 4, or it's going to be simply 2, in this case, AY. And that would be the tangent component. Do you all agree, class? I'm trying to make it easy. Does he ask for H field and B field, or just H field?
Just H field, just H2.
Does everybody follow me? Now, here we're going to use the second formula that he has in his book. You don't have to do it this way. But he has A21 crossed into H1 minus H2 is K. Does he show that? If you look, if you have your books on page 259, there's a picture in figure 4.39. Show A21 is AN, and I don't know if you must say it's somewhere in there. Well, he says it right below 4.76. And what I'm going to say is, I'm showing you this, but his A21 is this vector. It goes from region 2.
How is it that both the tangent and the normal component are both in AY?
So again,
You have both the tangent component and the normal component being AY, but that doesn't,
wait a second. I'm
that
sorry.
doesn't make sense.
I have what?
You have both the tangent and the normal component is AY. Because you said that, you said that's the tangent component, right? Which is AY, but you also wrote the normal.
No, I'm saying this is the normal component. This is a unit vector pointing from region 2 to region 1. If I misstated myself, I'm sorry. It's just perpendicular to the actual surface separator. That's all I'm sorry about it. That's the right H field, I hope. If you look in there,
Yeah,
see if that is the Y component of the H field.
It is.
All right, now the next part, what he has in his book, now that's a little different than I'm used to seeing it, but he has A21 is a unit vector that goes from region 2 towards region 1. Can you all see? And he'll have this form of it. He'll have A21 crossed in it, and he'll have H1 minus H2, and over here it's going to be K. Can you all see that? I'll give you that equation, because some of this stuff, he doesn't really go through a formal proof of it, he just states it explicitly. You all see this, class? How many have your books here? If you look, can you see that equation? Now, he doesn't, in the drawing, he has AN. He doesn't show you A21. I would put in there in that drawing A21, just so you have that there in front of you. Because normally, the way I do it this slightly different, and I don't want to confuse you. All right. Now, A21 here is going to be what, in terms of its actual vector sense?
Negative AY.
What? Negative AY. You're right. You all see this, class? It's pointing in the AY direction. It's got to be, but it's negative sense, negative, right? So it's minus AY. I'll put this as minus AY. I'm going to go ahead and do the whole formula. So this is minus A1 crossed into. Now H1 we have. One thing you'll notice, since that's AY, let me ask you this. Do we need to include that Y component? Why not? You're right.
Because they share the same.
The cross product of AY cross AY, give me 1 second. AY cross AY is 0. You see how this is a cross product right here, class? All with me? You don't need the AY component there. It's going to get crossed to 0. Can everybody follow me? So I don't need that. When I take a look at H1, Jeremiah, you had a question?
Could you review why, what is UR or UR something?
Mu relative is the relative permeability, right? It'll have a value from 1 upward, but it has to do with the material, it has to do with the materials we use. And these are arbitrary values. He's just showing you a theoretical problem. Did you have a question, anybody else? I'm trying to just do this, I'm trying to do it methodically. So here I got A1 and H1 over here. We won't need the Y component. I could put it in. Put 2AX plus 6AY for AZ part. 2AX plus 6AZ, right? And then Y. Minus, and it would be H2, and this would be H2X AX minus H2Z, Z component, right? And it would be AZ is equal to K, and I'm running out of room. I'm going to do the cross product before I put the value of K in. But can everybody follow me? It's basically keeping the books right on this one. It's not conceptually hard, you just have to keep the books. So if we do this, before I put K in, let's do this cross product right here. So I have, really, AY crossed AX is what? Minus AZ, right? But there's a minus sign. Do you all agree with this class? So it'd be AZ. And I'm going to have AZ here. And if you look, I have a 2, right? And then I have, now you can see that AY cross AX here gives me minus AZ, but I got, it's going to be minus. So it's minus H2X here, plus, I'm trying to do, can you all follow me what I'm doing here? I'm grouping things that have the same coefficient AX. Then I have AY cross AZ, which is AX, right? So, but there's a minus sign, so I have, it's going to be AY cross AZ is going to be AX, so it's minus 6, and then AY cross AZ will end up with a plus value here. Can you all see this, class? So it's going to be minus that plus H2Z, and all this has got to be equal to the surface current, this is AZ. And the surface current is 2AX, right? Minus 2AZ. Now, can everybody follow me on this? Wait a second, did I do? That should be AZ and AX. My bad. I'm sorry. AX, my bad. Y'all agree with that, class? I mean, follow me what I'm doing. And again, we're just going through and trying to keep the books on this one is the way I like to say it. Just trying to be correct in the way I'm doing it from here on out. It's easy to get casual and sloppy. So one thing I can see is 2 is the AX component is equal to those two things. Let me put this over here. So I have, let's see here. For the AX term, I have minus 6 plus H2Z is equal to, that's 2, right? And so that's the Z component is going to be equal to, looks like it's 8 amps per meter squared. And then, I'm sorry, 8 amps per meter. And then we have 2 minus H2X equal to, and for the AZ component, it's minus 2. So that means H2X is going to be equal to 4 amps per meter. You all agree with this, class? Is that the answer, by the way? Now, the real thing with these is just making sure you're careful with the signage, with the unit vectors and stuff. And also remember, that second part is a minus, and that vector has an HX and HY component. You all follow me? Just put them in there and you'll be fine. Do those problems a couple times. That's a good problem. Did this answer your question? I mean, did you have more or not? Okay. Really, with boundary conditions, they're irritatingly simple, but you can really fall on your face if you're not careful with the signs. I'm just being honest with you. And you're right, B normal 1 is B normal 2. I'm sorry, I thought that problem did ask for the H fields and without that surface current. Did you have a question back there anyway? Okay. Now, next, what I wanted to cover today, we're sort of moving into chapter 5, and I will put the solutions up. Just give you a bigger attention. So everything in here from here on is going to be accounting for time variation of the electric and magnetic fields. And I want to say this too. One important thing is to understand Maxwell's equations first and how everything else falls out of it. This is important. Now, if you have a physics background, some of this you'll, I know we have one person that's got it in physics here. This will be sort of things you've seen over and over again. You can almost get bored with it, but you have to understand fairly well. And I want to tell you one other thing. Now, I don't really run into this much, but I used to. There are systems of units. We use the SI or MKS system of units. The English system of units is a little different. And sometimes you'll see papers and things where they'll have C and 4 pi terms all over the place for Maxwell's equations as constants. Don't worry about it. Stick with MKS and you won't ever have a problem. Now, you understand, like, how many have had thermodynamics here? You all know the BTUs and, steam tables always bothered me. And the unit conversions are the thing that got me more than any of that. And I've had a lot of thermodynamics. But here are the things that we always go for. These are the 2 equations. I'll put 3 here we always use. We use curl of H, I just put this down, is J plus the partial of D with respect to T. And then we use curl of E is equal to minus dB dt. Those 2 are always really the starting points. There are relationships, of course. J itself is sigma E. Please make sure you know this. D is equal to epsilon D. And really B is mu H. And one more is divergence of D is equal to rho V. Now that sort of takes care of everything in terms of the interconnection between E, H, and D, and the 2 things that really define all the inner workings of the things, how J and D and H and E all interact. Now something else, there's a term, I like to make sure I understate this at least twice. This has a name, this particular curl of H law. Do you remember what it is? Ampere's law. Sometimes they call it Ampere's circular law. What is this called, the curl of E? Michael Faraday's law of induction. Both are based on measured data, but they work exactly, which is amazing. Okay, now, when we have these 2 things, we did this one for actually charge decay. We took a divergence to get the charge decay, right? Now what we're going to do is work on the second one right here, Faraday's law of induction. And we're going to see how that actually allows us to calculate transformer action. You know how a transformer works, basically, right? You have to have AC, or has to have a time variation of voltage to get any kind of transformer action that's effective. So how does that work? And here's how it works. If you take that equation, you take curl of E, and you're going to say that's equal to minus dB dt. And this is going to be a little abstract. Now we're going to integrate those over a surface. So I'm just putting a surface here. I don't think there's any easy way to do this. This is my surface S right here that I'll talk about in a second. So I'm going to integrate the curl of E dot ds over that surface, and that's equal to minus ddt of the integral of V dot ds over that surface. You all with me? Just assume for a second. I'll try to be clear. Suppose X is out of the board, Y is in this direction, and Z is up, and this is going to be in the XY plane. And assume I have a B field coming out of the board. Just B is some B naught of T in the AX direction, and that would be Webers per meter squared as the units. and then I'm putting this up here because I'm going to need it in a second. I can say the differential surface here would be equal to really dz dy 8x. Can you all follow me? I'm just trying to show you a theoretical surface in the xy plane to make it easy, give you a visual on this. Now, when I go ahead and integrate this over a surface, this is Stokes' theorem. How many have had Stokes' theorem? One? No? Somebody else I know has in here. I think he has. I don't even see the guy. Who had physics before? Who got a physics degree? Might not say anything.
It was
I guess he's gone.
He's not here.
He's skipped. Anyway, this is equal to the integral. It's the counterclockwise integral over the closed path of E dot dl around the rim. What I'm really saying is this. Integral of a curl of a function over surface area is the same thing as the integral of that field value, not the curl of it, right around the rim. So if you took a look at an integral of the E field around this rim in this direction, you would get this value. What we call this is the voltage. This is a voltage, but it's called the EMF because it's an electromagnetic force. It's actually induced in this loop not by electrostatic charge, but by a time-varying magnetic field. Y'all follow me? And that'll create a voltage, and it's important you put the polarity here, plus to minus VEMF of T. So if you integrate the E field in a counterclockwise direction all around that loop, assume it's made of a copper wire or something, and there's a small little gap, the voltage that you would develop is this value. How many remember this from physics? 1, 2. I mean, it should have been something that you got. I mean, this is sort of a standard thing in physics. So if you get this right here, you'll see that the VEMF of T is really, now I'm going to jump right over here, is minus d dt of the integral of b dot ds. So what is the integral of b dot ds usually shown as, or we have talked about? That's the magnetic, or really, I use that psi magnetic of T. That's the flux, and the units are Webers. Do y'all remember that, class? Remember, we just talked about magnetic flux with magnetic circuits. Do y'all remember that? Now that's just for one turn. For more than one turn, you would multiply this value V by the total number of turns. See? But if I look at this, this is equal to the flux. And we're going to go and just use the symbol. So now I want to calculate that magnetic flux for this theoretical problem right here. Can you see it or not? Everybody, are you okay with it? And if you can't, let me know. But I'm trying to just show you. I know this is kind of abstract, but this is the beginnings of something that you will see as you go through the problem. So now I need to calculate this integral of b dot ds, and I'll do it over here. You're going to see that this is not a big deal. It's important you see it and appreciate it. By the way, this is always a trivial integral. If b is not very spatially, when I look at the integral of b dot ds over that surface, just take a look at this for a second. I have the b field coming out of the board. I just have it as b0t in the ax direction. I'll put that in here. So it's b0 of t ax dotted in with ds. Does everybody agree that that's the differential surface? It's got to be what? dy dz, right? And then it's got to be in a perpendicular direction, which is ax if you use the right-hand rule. So it's going to be dy dz ax. Ax dot ax is 1, right? What this really is doing, the way I've developed it, if you integrate over dy dx over that, you get the surface magnitude of the area. Do you all agree? So now you can see that this is simply the area times b0 of t. And that would be the magnetic flux as a function of time. That would go there. Please just watch. Y'all with me? Now you have to take a time derivative. to get the voltage, right? And put a minus sign too. So that means the actual VEMF of T is minus the time derivative of the magnetic flux with respect to T. And that means it's simply going to be minus A times the time derivative of the B field with respect to T. And this would be in volts too. But you'll notice there's a minus sign. Everybody? Can you all see it? I circle mine a lot of times when I'm doing work. What that means is when I get this value, when I take this value, A times dB dt, whatever it is, I need to take that and put a minus sign there and put it here, which really means these two terminals will be flipped in a sense. You all with me? Let me see this, because if it's, think about this. If B naught T, say it's just equal to 5T. Time derivative of that would be 5, right? With respect to T. 5 times A. With a minus sign means minus 5 times the area. Means these two terminals would, you'd flip them if you wanted to pause it. Everybody, I'm trying to make this clear to you. You've measured, you've had meters, right? Everybody used meters. If you take a meter and put it on a car battery and you put the positive lead on the negative terminal, negative lead on the positive, you read negative 12 volts, right? That's what I'm trying to say here. The polarity is important, okay? And you'll do some problems with this in mind. So now I want to do a problem that'll really show you how this applies. This is what I'm really trying to do to you. This is stationary EMF, but this is the reason transformer coils work. Now, what do you see happening right here if the B field is not time varying? What's the derivative of constant? With respect to 0. There's no induced voltage. That's why transformers have to have time varying current and voltage to either step up or step down a voltage and current. You all with me? That's very important. You can't do them for DC. You can take DC current and then you can chop it. Basically, you can cause a transient effect and then you can put that through the transformer, but you can't just get DC and change the voltage. Okay, now to do a problem where this applies. And this is a classic problem. Wentworth's book does this. Some of you may have seen this. I'm sure you have. I just don't know where you saw it. Hopefully in physics. I don't think there's anything in the lab you'd see this before. So here's the classic problem. You got the z-axis, and now I have a current in this direction, and I'm going to call that I of t is 20 times, say, sine of 10t amps. It's going in the positive z direction. Can you all see this? Now, I'm going to assume that I've got a loop out here in the plane of the board, more or less in the zy plane. That's x, and this is y. I've got a, matter of fact, let me move that out. I'm going to put a loop in here in the plane of the board, but I want to show you how these things, how that law is actually used. I'll put it out here. And I'm going to make this thing have a height h, and I'll make it have a width w, and I'll say out to this point, it's simply a radius a. And what my goal is to find the voltage right here, VEMF as a function of t. Can y'all follow me? Everybody follow me on this? So for starters, in order to do this, I first have to get the B field as a function of position this way. Do y'all see this, class? Now, I didn't use cylindrical coordinates. I chose this is x and this is y, and that loop there is in the actual zy plane at x equals 0. Can you all imagine this? So what would the B field be? The B field as a function of t in position would be 1. Well, it has to be mu zero. Let's assume we're in free space, right? Then it's a function of I of t, and I'm just going to put I of t right here. I have to divide that by 2 pi, the radial distance, and I'll call the radial distance in this case y. Usually it's rho, but I'm saying if I want at radial distance y way, if I want the actual B field here, that's what I'm after. And you'll notice the B field would be going into the board. If the current's going up, right, the B field would be going in. You all see this on this side of the board? How many see this right here? All right. Now, that's the magnitude. It would be in the what direction, class? If x is coming out of the board, this is going in the minus ax direction. The units of this would be equal to Webers per meter squared. All right, that's the B field. Now, think about it. We actually need the total flux through this loop. That's what we need, right? So we need the integral. The integral of the B field dot ds over that surface. I think I'm out of time. But you all follow me? I'm going to see what I'm doing. We've done these kind of problems, if you remember them, right? For mutual inductance, do you remember we got the flux from one system through another system? Okay, so what's this going to be? I mean, I'm going to just say this. If you look at this, the mu 0 and 2 pi come out in front, right? Over 2 pi comes out in front. That's only a function of time, so I can take that out in front, I of t, right? And then I have minus ax. What is this differential surface right here going to be? D what? dy dz, right? In what direction? Positive ax. Can everybody follow me on this one? And the way you get it is, this is a right-hand coordinate system. So on the side of the board, you want the actual surface vector. Just grab it with your right hand, your thumb will point in the direction. You see it's positive ax? So this is going to be dy dz, positive ax is ds. So now I have to come in here and I have to do this integral. The B field has a minus ax sense. It started with something with a positive ax, and it's got dy dz. It's a double integral. And if you do this, you can see it's going to be h. I'll just finish it right here. It's going to be mu 0 over 2 pi times the I of t that I stated there. And then it's going to be times h. And when we do the integration out in the y direction, we're going to get a natural log, because this is actually going to have divided by rho, because it's in this direction. That's the B field. I mean, divided by y. And so you're going to get a natural log of really A plus W over just A. Just let me finish here. That's going to be the flux. Do y'all follow me? If we do the integration, you'll see it. Y'all with me, class? I didn't bother to replace I of t with actual function. Now you need the value of the time derivative of that. That's straightforward, because that's a straightforward derivative, doesn't it, class? It's going to be 20 times cosine of 10t, and the 10 will come out in front. Want it, class? So it's 200. Then after that, you can say that's VEMF, but it's got a minus sign, and you can get this voltage. I'm sorry, I'm out of time. I'm about a minute over, I think. But you all take, can you follow me? Now I'm going to give you homework about this. Send me that thing about, I'll put the solutions up. I'm going to do that next. And I'm going to my office if you need to see it. And there will be a quiz Wednesday, right? And that will include the homework for today. You all with me? So I want to make sure you do this in the prior homework. It won't be on magnetic circuits. It'll be on chapter 5 stuff. We'll deal with magnetic circuits and boundary conditions later.